Imagine driving like 70 miles an hour down the highway.
Mm.
And suddenly, deep inside your electric vehicle's computer, a sensor reads a microscopic drop in voltage.
Yeah.
Your car now has exactly 60 milliseconds, which is, I mean, less than the time it takes you to blink
Right.
to decide whether to gracefully cut the power or accidentally lock your wheels and send you spinning into traffic.
It is a totally terrifying window of time. I mean, the difference between those two outcomes isn't decided by a reinforced steel bumper or an airbag.
Right.
It is decided by lines of code, the molecular structure of a tiny ceramic capacitor, and the friction coating on a single bolt.
That invisible high-stakes engineering is our mission today. So we are taking a deep dive into a stack of highly technical engineering documents. They detail the functional safety and diagnostic strategies for modern hybrid dual-motor power control systems, or PCS.
Yeah, those are very dense documents.
They're very, and to make sense of this, we're going to focus entirely on one specific critical failure mode that's pulled from a 45-point diagnostic checklist in these sources. It's labeled simply B05, DC link under voltage. And that's under the inverter and power stage faults category.
Which I know sounds incredibly dry, but the source documents explicitly tie this fault to what the automotive industry calls an ASIL D safety goal.
So let's translate that for anyone not steeped in automotive safety standards. ASIL stands for Automotive Safety Integrity Level, and the D means it is the highest, most stringent classification possible.
Exactly.
We're not talking about the radio acting up or, a check engine light coming on.
No.
An ASIL D failure means we're looking at the potential for a total loss of vehicle propulsion.
Right.
Or even worse, a scenario where the massive electromagnetic force of the motors actively fights the driver, like locking the wheels at highway speeds.
Right. The margin for error is effectively zero.
Yeah.
What's fascinating here is that today's EVs are essentially rolling supercomputers dealing with massive lethal amounts of raw electrical power. If the computer makes the wrong call, or if a physical component fails and the computer doesn't catch it fast enough, the physics of the vehicle become incredibly dangerous.
Wow. So before we get into how the car's brain handles this crisis in 60 milliseconds, I want to understand the physics of the crisis itself.
Okay.
We need to do a root cause analysis. The documents outline 4 distinct physical dimensions, like 4 completely different ways that this DC link under voltage fault can trigger.
Yeah, they really cover all the bases.
So I want to look at the first one, which is simply categorized as a high voltage disconnection. If I'm tracking the terminology, this involves the main battery suddenly cutting out.
Yes. So think of the high voltage battery pack as this massive reservoir of energy.
Right.
It is physically connected to the rest of the car's high voltage system, like the inverter and the motors, by these heavy-duty mechanical relays. They're called main contactors.
Okay.
Now, there is an independent computer monitoring that battery called the Battery Management System, or BMS. And the BMS is incredibly paranoid.
As it should be.
Exactly. If it detects a crash or a severe overcurrent situation or even just a slight breakdown in the electrical insulation shielding the chassis, it will instantly fire those contactors open.
So it physically severs the connection to protect the battery and the passengers from electrocution or fire.
Right. Just completely cuts it.
That makes logical sense. Like if there is a catastrophic event, you cut the main power line.
Yeah.
But if the car is currently executing a high-power maneuver, say you're accelerating hard onto a freeway,
Right.
what happens to the motor when you just sever the battery connection like a guillotine? I mean, the motor is still physically spinning and demanding power.
It creates absolute electrical chaos. Even though the battery is gone, the inverter and the motor are still operating under the assumption that they have unlimited power available.
Oh, wow.
So they pull from the only place left, which is the internal circuitry of the power control system itself. Specifically a component called the DC link capacitor.
Okay, let's unpack this. What exactly is the DC link capacitor doing in this scenario?
A capacitor is like a very small, incredibly fast temporary battery. Its normal job is to smooth out the electrical ripples between the main battery and the inverter, just making sure the power flow is clean.
Right.
But when the main battery suddenly disconnects, this capacitor is the only energy reservoir left.
And it's tiny.
Exactly, because the motor is demanding hundreds of amps of current to keep accelerating it. It effectively sucks that capacitor dry in a matter of milliseconds.
So the voltage across the main power lines, the bus bars, just falls off a cliff.
Yes. The engineering documents map this out mathematically as a parabolic voltage drop.
It sounds a bit like unplugging a massive industrial vacuum cleaner from the wall while it's still running at full speed.
Yeah.
The motor doesn't just stop instantly, right? Its inertia keeps it spinning, and it violently drains whatever residual electrical power is left inside its own internal wiring until it just chokes out.
That is a very accurate way to visualize it. And
Yeah.
in the car, when the voltage plummets like that, it triggers an immediate massive undervoltage fault. The system has suddenly lost its driving force. So that is root cause number one. The power is literally amputated by the safety system.
Wow. But the second root cause seems far more insidious because nothing actually breaks or disconnects. The documents point to the chemistry of the battery itself fighting against the driver's demands.
Yes.
The specific scenario outlined is driving in extreme cold, like negative 30 degrees Celsius, and suddenly pushing the accelerator to the floor.
This comes down to the fundamental limitations of lithium-ion chemistry. When a battery pack gets that cold, the liquid electrolytes inside the cells become incredibly sluggish.
Okay.
The internal resistance of the battery spikes exponentially. The chemical reactions simply cannot happen fast enough to push the electrons out of the battery terminals.
So the energy is in there, but it's trapped behind this massive wall of internal resistance.
Right.
But the car's motor doesn't know that, right?
No, it doesn't. The motor controller operates using a highly advanced algorithm called field-oriented control, or FOC. Right. When you floor the pedal, the FOC algorithm is trying to maintain the absolute perfect angle between the magnetic fields in the motor's rotor and stator to give you maximum torque.
Okay.
And to do that instantaneously, the FOC demands a massive sudden spike in current. It's a transient current demand.
The motor is pulling as hard as it can, but the frozen battery is acting like a clogged pipe.
Exactly.
It can only drip out power when the motor is asking for a fire hose.
Right. And because the battery can't deliver that massive flow instantly, the system once again pulls from that poor DC link capacitor to make up the difference.
Ah, so we're back to the capacitor.
Yeah. The FOC algorithm pulls energy out of the capacitor significantly faster than the freezing battery can refill it. This creates a severe transient voltage sag.
Okay.
It is a temporary drop, but if it dips low enough, the car's sensors will read it as a critical failure.
It's fascinating that the system's own desire to perform optimally, like that FOC algorithm demanding perfect torque, is what actually causes the voltage to crash when the battery is cold.
Yeah, it's kind of ironic.
Okay, so that is root cause 2. The third one, though, feels like a completely different animal. The source documents refer to it as an auxiliary low-voltage sag. I'm going to call it the 12-volt hiccup because it seems to be an optical illusion for the car's computer.
Yes. If we look at the broader architecture of an electric vehicle, it is a great example of how legacy technology is still deeply intertwined with cutting-edge engineering.
Right.
Your EV has a massive 400-volt or 800-volt high-voltage battery to drive the wheels, but tucked away under the hood, it still relies on a standard old-school 12-volt lead-acid or lithium battery.
Which is to run the computers in the headlights, right?
Yeah, exactly. The sensors and the low-voltage electronics.
Which always seems wild to me. Like you have this massive power plant, but the brain of the car runs on the same voltage as a golf cart.
It separates the lethal propulsion power from the delicate logic circuits. That's the reason.
Okay.
But here's the vulnerability. During the vehicle's startup sequence or under certain heavy accessory loads like the power steering pump and the seat heaters kicking on simultaneously.
Yeah. That 12-volt battery can briefly sag under the strain. Oh. The documents note that the voltage on this auxiliary line can temporarily drop down to 6 volts for a duration of just 20 milliseconds. 20 milliseconds is, barely a fraction of a blink.
Barely anything.
Why would a tiny dip in the low-voltage accessory battery cause a critical failure in the 800-volt propulsion system?
Because of how the high-voltage sensors actually work, they need a baseline.
Right.
That 12-volt system feeds into linear regulators on the control boards, which step the voltage down to create incredibly stable 5-volt and 3.3-volt reference voltages.
Right.
The high-voltage sensors use those 5-volt and 3.3-volt signals as a measuring stick, basically, to calculate the massive 800-volt lines.
Okay, let me see if I have the physics right here.
Sure.
If that 12-volt supply sags to 6 volts, the regulators might struggle, and those 5-volt reference signals might momentarily dip as well.
They do dip, and if the sensor's baseline measuring stick suddenly shrinks, its math gets completely thrown off.
Oh, wow.
The analog to digital converter, or ADC, will look at a perfectly healthy 800-volt propulsion battery. But because its internal reference voltage just shifted, it will output a reading that says the high voltage has plummeted.
Ah, so it's a phantom fault.
Exactly.
The main battery is fine, the capacitor is fine, the power to the motors is flowing perfectly, but the sensor's having a hallucination because its own life support system flickered for 20 milliseconds.
Yeah.
It looks at the high voltage and screams to the main computer the voltage is crashing.
It is a false alarm entirely generated by a momentary hiccup in the low voltage support system.
Right.
But the main computer doesn't inherently know it's an illusion. If it takes that reading at face value, it might execute an ASIL shutdown on the highway when absolutely nothing is wrong with the powertrain.
We will definitely need to get into how the car figures out it's being lied to.
Definitely.
But I want to hit the fourth root cause first because reading the documents, this one genuinely threw me.
Yeah, this one is interesting.
The first three causes make sense, right? Power cuts, frozen chemistry, sensor hallucinations.
Right.
But this fourth one is purely mechanical. It comes down to the physical assembly of the car. Specifically, the documents highlight the danger of a single incorrectly coded bolt.
This is where we bridge the gap between electrical engineering and physical metallurgy.
Okay.
It revolves around a phenomenon called axial preload loss.
Axial preload loss.
Right. So inside the power control system, you have massive copper bus bars carrying hundreds of amps of current. These bus bars are bolted to the terminals of the DC link capacitor and the inverter modules. The amount of clamping force, like the physical pressure squeezing those metal surfaces together, which is the preload, is absolutely critical to electrical conductivity.
And the sources explicitly state that this failure mode triggers if a manufacturing facility uses standard bolts instead of bolts that have a specific phosphate coating.
Yes.
I understand the clamping force is important, but why would a microscopic layer of phosphate on the threads of a bolt dictate whether my car dies on the highway?
It all comes down to friction. When a robotic arm or a factory technician drives a bolt into a threaded hole, they are applying a turning force, which is torque.
Right, torque.
The torque wrench is calibrated to stop turning when it hits a specific resistance, say 10 Newton meters.
So the machine turns the bolt until it feels 10 Newton meters of pushback, and then it clicks and says, done, it's tight.
Right. But if the bolt lacks that slippery phosphate coating, the raw metal threads scrape against each other. The friction between the threads is abnormally high. So the machine starts turning the bolt, the friction spikes immediately, and the torque wrench hits that 10 Newton meter limit very early.
And the machine stops and registers the bolt as perfectly tight.
Exactly.
But the energy of the twist was completely wasted on fighting friction in the threads. It wasn't actually used to pull the head of the bolt down and squeeze the copper plates together.
The clamping force is incredibly weak. The system thinks it's secure, but it's barely holding on. Now take that weakly clamped joint and put it in a car.
Yeah.
Add the constant aggressive vibration of driving over potholes and rough asphalt. Those heavy copper plates start to subtly vibrate and micro-move against each other.
And as they vibrate, the microscopic points of contact between the two metal surfaces start to wear down or oxidize.
Yes. The contact resistance at that specific joint slowly degrades. Normally, that joint should have a resistance measured in microscopic microohms.
Right.
But because of the micromovements, it slowly spikes up to milliohms and eventually full ohms.
And when the driver floors the accelerator, the motor is trying to pull hundreds of amps of current through a joint that now has high electrical resistance.
Exactly. Pushing that much current through a high-resistance bottleneck creates massive localized heat. I mean, it acts like a heating element in a toaster.
Oh, wow.
But more importantly for our diagnostics, it creates a massive voltage drop right across that loose joint according to Ohm's law.
Right, Ohm's law.
So the voltage sensor, which is reading the line just downstream of that bolt, sees the voltage plummet. It assumes the entire high-voltage bus is failing.
So you get a localized undervoltage emergency, completely triggered by the physics of a single bolt that didn't have enough lubricant on its threads in the factory.
Yes.
That is incredible. The idea that friction on a thread could strand you on the shoulder of the highway.
It really illustrates how intertwined the physical assembly is with the electrical logic. So we now have our 4 triggers.
Right.
The emergency disconnect, the frozen battery fighting the FOC algorithm, the 12-volt phantom fault, and the loose bolt. The physical problem has occurred.
Which brings us to the next massive challenge outlined in the documents. The technical architecture required to detect this drop.
Yeah.
We established earlier that the car has exactly 60 milliseconds to figure this out and react. How does the car's brain actually see the high voltage system safely?
It's complicated.
I mean, you can't just run an 800-volt wire directly into a delicate silicon microprocessor. It would vaporize.
No, definitely not. It requires a specialized layer of hardware called high isolation sensing. The architecture detailed here is really fascinating. We need to take 400 or 800 volts of raw legal direct current and feed an accurate representation of it into a microchip that runs on 5 volts.
Without electrocuting the microchip.
Yes. So the first step is using a network of precision resistors. These act as a voltage divider, effectively shrinking that massive 800-volt signal down to a tiny microscopic analog signal, usually swinging between -1 volt and +1 volt.
So it creates a completely proportional miniaturized reflection of the main power line.
Right.
If the 800-volt line drops by 10%, this tiny 1-volt signal drops by exactly 10%.
Exactly that. But the computer can't read analog waves. So that tiny analog signal is fed into a component called a delta sigma modulator.
Delta sigma modulator, okay.
What this does is measure the analog wave millions of times a second and convert it into a high-frequency digital bit stream.
Okay.
So a continuous flow of ones and zeros representing the exact voltage level.
Okay, so we have digitized the voltage,
Right.
but it's still physically connected to the high voltage circuit. How does it cross over to the computer's logic board?
It passes through a digital isolator. This is a physical barrier on the circuit board. It's a literal gap.
Like empty space.
Yeah. The ones and zeros are converted into microscopic pulses of light or sometimes high-frequency magnetic fields that shoot across the gap to a receiver on the other side.
Wow.
This completely separates the high-voltage physical environment from the low-voltage computer brain.
That is a brilliant piece of hardware engineering. The data crosses the moat, but the lethal voltage cannot.
Exactly.
And the documents specify the recipient of this data is a microcontroller known as the AURIX TC3XX.
Right.
Why this specific chip? Why not just use a standard processor like you'd find in a high-end laptop?
Because a laptop processor isn't designed for ASIL D safety standards. I mean, if your laptop has a math error, your spreadsheet crashes.
Right.
If a car's processor has a math error, the brakes lock up. The AURIX TC3XX is an automotive-grade microprocessor built with something called lockstep architecture.
Lockstep architecture.
It actually has redundant processing cores that run the exact same calculations simultaneously.
So core A and core B are doing the math at the same time, and they constantly compare answers.
Yes.
If a stray cosmic ray or electromagnetic noise flips a bit in core A, its answer won't match core B.
And the chip instantly knows there's been an internal processing error and flags a fault rather than executing a corrupted command. It is paranoia built into the silicon itself.
Wow. So the AURIX chip safely has the data.
Yeah.
It knows the voltage reading is dropping. But this circles back to the 12-volt hiccup we talked about earlier.
Right, the optical illusion.
Exactly. The sensor is reporting a voltage drop, but it might be lying. If a sensor says the power is dying, my intuition says, just shut the car down instantly.
Yeah.
Cut the power, better safe than sorry. Why does the car hesitate?
Because better safe than sorry in an electric vehicle traveling at highway speeds does not mean shutting down. Well, imagine you're in the fast lane passing a semi-truck at 75 miles an hour, and the car decides to completely sever all propulsion because of a 20-millisecond blip in a 12-volt battery.
Oh, man.
That sudden unexpected loss of power is incredibly dangerous. It could easily cause an accident. The car must be absolutely certain the fault is real before taking drastic action.
Right, it has to interrogate the data.
Exactly.
How does the AURIX chip figure out if the sensor is telling the truth or if it's a phantom fault?
It uses software logic called a power plausibility check. The software essentially acts as an incredibly fast, unforgiving accountant.
Okay.
It constantly cross-checks the math across different systems. It calculates the total DC electrical power entering the inverter from the battery, and it compares it to the total AC mechanical power leaving the inverter and going to the electric motor.
So it's relying on the basic laws of thermodynamics. Energy in must equal energy out.
That is the foundation of it. If the voltage sensor is screaming that the input voltage has plummeted to near zero, but the speed sensors on the motor confirm that it is still happily outputting maximum horsepower and accelerating the car,
Yeah.
the math doesn't match. Energy cannot come from nowhere.
Right. The computer realizes, wait, if the voltage is really this low,
Yeah.
there is physically no way the motor could be pushing this hard. Therefore, the low voltage reading has to be a lie.
It catches the sensor in a lie using physical reality. So instead of slamming on the digital brakes and stranding you in the fast lane, the software flags the specific voltage sensor as faulty,
Okay.
keeps the power flowing using backup logic, and triggers a yellow warning light on your dashboard telling you to get the car serviced.
It uses physics to double-check the electronics in real time.
Exactly.
That is remarkable. But what happens if the math does match?
Wow.
Like, what if the voltage really is dropping, maybe because of that frozen battery or the high voltage disconnect, and it's a genuine failure?
Right.
The motor is losing power. The voltage is crashing. What does the system do in those remaining milliseconds?
Then the system activates its two-tier defense protocol. It doesn't just panic and shut down. It handles the situation progressively.
Okay.
Level 1 is the warning and mitigation phase. Let's say the system normally runs at 400 volts. If it sees the voltage drop into the 200 to 250 volt range, it realizes the power supply is struggling.
It knows a crisis is starting, but it's not fatal yet.
Right. So it intervenes to reduce the strain. The software smoothly commands the inverter to reduce the motor torque. The documents note it drops the torque by 500 newton meters per second, effectively limiting the car to about 30% of its maximum power.
It's like the car realizes it is sprinting too fast while holding its breath.
Yeah.
So to keep from passing out, it forces itself to slow down to a light jog just to catch its breath.
Yeah.
It is actively trying to stop the voltage from crashing completely by reducing the demand.
Easing off the throttle electronically to give the battery pack time to recover from the transient spike. It's a very elegant mitigation. But if that doesn't work, or if the voltage drop is too violent, like the main battery completely disconnecting, we hit level 2.
Okay.
The fatal threshold.
This is the point of no return.
If the voltage drops below 150 volts, the car has reached a critical safety limit. The control chips simply won't have enough voltage to drive the heavy power transistors.
Okay.
And this is where that fault-tolerant time interval, the FTTI, comes into play. The system has exactly 60 milliseconds to save itself before the hardware loses control.
Less than a tenth of a second? What action does it take?
If we connect this to the bigger picture of vehicle dynamics, the command issued in this moment is the most critical decision the car makes.
Okay.
When the inverter is forced to shut down the spinning motor, there are two primary ways to do it. One strategy is called active short circuit, or ASC. The other is active open circuit, or AOC.
Right. Our sources dedicate a significant amount of ink to emphasizing that the system must choose AOC over ASC in this specific undervoltage scenario.
Yes.
If both are shutdown methods, why is the choice so critical?
Because the physical results of those two commands are entirely different. If the system were to trigger an active short circuit at highway speeds, it intentionally shorts out the motor windings tying them together.
Okay.
This stops the flow of power from the battery, but it turns the spinning electric motor into a massive, instantaneous electromagnetic brake.
It would essentially be maxing out the regenerative braking instantly.
It would be so violent, it would literally lock the wheels while you were driving 70 miles an hour.
Oh, man. That would cause an uncontrollable, catastrophic spin-out. You'd lose all steering and traction.
Which completely violates the ASIL D safety goal.
Right.
So instead, within that 60 millisecond window, the system must recognize the undervoltage process, the math, and execute an active open circuit.
AOC.
Yes. AOC is effectively freewheeling. The computer completely and instantly shuts off the gate drivers to the power transistors, essentially opening all the switches.
Just cuts the electrical connection to the motor entirely.
Exactly. By opening the circuit, the electrical current inside the motor smoothly decays to zero. The motor stops providing thrust, but crucially, it does not break.
Right.
The electromagnetic field collapses gracefully, and the wheels are allowed to freewheel.
Giving the driver the ability to maintain physical steering control and coast the car safely to the shoulder of the highway.
The engineering logic here prioritizes the physical kinematic stability of the car above all else. It's not just protecting the delicate electronics from a voltage drop, it is deliberately failing in a way that keeps the human in the driver's seat alive.
Wow. It is an invisible safety net, catching the physics of the car in 60 milliseconds.
Yeah.
So we've covered the physics of the failures and the brilliant software and hardware architecture that diagnoses and mitigates them on the fly.
Mm-hmm.
But obviously, automotive manufacturers don't want these faults happening in the first place.
No, definitely not.
That brings us to the preventative side of the documentation.
This is where we get into the heavy industrial engineering protocols. The documents detail the DFMEA and the PFMEA.
Okay, let's break down those acronyms. Design failure mode, And effects analysis and process failure mode and effects analysis.
Right.
In layman's terms, how do we design the hardware perfectly so it doesn't break, and then how do we build it perfectly in the factory so we don't introduce flaws?
Exactly. Let's start with the design defenses, the DFMEA. How do engineers lock down the circuitry at the drafting table so these sensor hallucinations and power drops don't occur?
Yeah.
The documents highlight a specific component requirement for the voltage sensing circuits that I found fascinating. It mandates the use of Class 1 C0G or NP0 ceramic capacitors.
And the specific dielectric material used in those capacitors is calcium zirconate.
Right.
If I'm an engineer looking at a massive bill of materials, why am I forced to specify calcium zirconate for this tiny part instead of a cheaper standard ceramic capacitor?
Because the physical environment inside an EV inverter is absolutely brutal. I mean, it swings from negative 55 degrees Celsius when parked in a freezing climate to positive 125 degrees Celsius when the car is running hard up a mountain. Standard electronic capacitors change their physical properties when they get hot or cold. Specifically, their capacitance, like the ability to hold a charge, drifts wildly with temperature changes.
Wait, if the capacitor is part of the circuit that measures the voltage, and the capacitor changes its behavior based on the weather,
then the sensor's reading will drift. The main computer will look at the data and think the 800-volt line is dropping, but in reality, the high voltage is perfectly fine. The tiny measuring capacitor just got hot and changed its mathematical output.
it would cause yet another phantom undervoltage fault.
Exactly. But calcium zirconate is a highly specialized crystalline structure. It has essentially zero temperature drift across that entire massive temperature range.
Oh, wow.
Whether it is frozen solid or practically boiling, its electrical properties remain absolutely stable.
So they designed the hardware to be thermally invincible, so the software doesn't have to constantly second-guess if the data is skewed by the weather.
Furthermore, calcium zirconate has no piezoelectric effect. In standard ceramics, mechanical vibration, like the car driving over a bumpy road, actually physically deforms the crystal lattice, which generates phantom electrical noise inside the capacitor.
Seriously?
Yeah, calcium zirconate doesn't do that. By locking the specific material into the design, the engineers eliminate temperature and vibration-induced false alarms at the subatomic level.
That is incredibly meticulous.
It has to be.
The documents also outline a design feature I'm going to call the 20 millisecond hold-up circuit.
Ah, yes.
This directly addresses that 12-volt hiccup we analyzed earlier, where the auxiliary battery sags and threatens to shut down the logic boards. How do they design around that?
The engineers know that 12-volt supply is vulnerable. To prevent the high-voltage sensors and the critical gate drivers from instantly losing power and triggering an under-voltage lockout, or UVLO, they design a localized secondary power supply right on the circuit board.
So they build a tiny backup system.
Exactly. They use a secondary side LLC power topology with high-temperature electrolytic capacitors. Think of it as a tiny isolated reservoir of energy dedicated solely to keeping the brain chips alive. If the main 12-volt supply from the car suddenly drops to 6 volts, these hold-up capacitors instantly discharge their stored energy.
So they literally bridge the gap.
They keep the microprocessors and the gate drivers fully powered and executing math for just a little over 20 milliseconds.
Right.
By the time that hold-up power is finally running out, the car's main 12-volt battery has recovered from its sag, and the computer never even noticed the crisis happened.
The system is structurally designed to hold its breath just long enough for the transient event to pass.
Yeah, it's brilliant.
It really is. The documents also mention physical reinforcement at the design stage, using 3D thermal stress and vibration simulations and specifying rigid pins for the components.
Because all of this brilliant electronic logic is completely useless if the physical solder joints connecting the microchips to the heavy copper bus bars crack under the constant vibration of the road. Engineers run supercomputer simulations of how the board will warp and flex as it heats up and cools down over 10 years of driving, ensuring the physical connections survive the thermal expansion.
Which is the perfect transition into the manufacturing side.
Yes.
Because it is one thing to design a thermally invincible, perfectly simulated system in a CAD program.
Oh, yeah.
It is an entirely different beast to build 10,000 of them perfectly on a factory assembly line.
Very true.
This is the PFMEA, the process control. And reading this section, the factory floor sounds less like a traditional car plant and more like a semiconductor clean room.
It has to be. Let's revisit that loose bolt issue we discussed, the one that causes axial preload loss, massive electrical resistance, and localized voltage drops.
The non-phosphate coated bolt of doom.
To prevent that failure from ever leaving the factory, the manufacturing process controls are draconian.
Really?
Standard pneumatic tools like the air guns you see mechanics use are completely banned for assembling these high-voltage joints. They are too dumb. They just twist until they slope.
So what do they use instead to ensure the clamping force is perfect?
They use closed-loop servo screwdrivers equipped with torque angle tracking.
Torque angle, meaning the robotic arm isn't just measuring how much turning force it's applying, it's also tracking exactly how many degrees of rotation the bolt is making while that force is applied.
Yes. The machine is plotting a real-time graph of torque versus angle. It knows exactly what the physical resistance should feel like at every millimeter of the bolt's descent.
Okay.
If the bolt lacks the proper phosphate coating, the friction spikes too early.
Right.
The machine sees that the torque hit the maximum limit, but the angle sensor reports that the bolt hasn't turned enough times to be fully seated.
Oh, the machine instantly knows the thread friction is wrong and it rejects the part.
Exactly. It won't let a weakly clammed joint pass down the line.
But the process controls go even further upstream.
Oh,
right?
yeah. Before the robotic screwdriver even touches a fastener, optical character recognition cameras, or OCR systems, scan the incoming boxes of bolts on the supply line. If the camera's algorithm does not visually read the exact words phosphate coded on the supplier's label, the entire assembly station automatically halts.
It plays bouncer.
Yes.
It won't even let the wrong box of bolts enter the physical workspace.
All of this robotic paranoia is designed to guarantee one physical metric. The contact resistance of that joint must be less than or equal to 5 microohms. They are automating the absolute prevention of the root cause.
And the documents show they apply that same level of obsessive inspection to the printed circuit boards themselves. They mandate 3D X-ray inspection, known as AXI, on every single surface mount technology or SMT solder joint.
And this isn't random sampling. It is 100% inspection of every board.
That's intense.
The SMT joints are the microscopic blobs of solder that hold the tiny components like our calcium zirconate capacitors to the main logic board.
What exactly is the 3D X-ray looking for inside a microscopic drop of metal?
It is looking for voids, microscopic air bubbles trapped inside the solder when it melted. The process standard is incredibly strict. It dictates that the total voiding rate, the volume of air inside the metal, must be less than 5%. And on any single connection pad, it must be less than 1%.
Why are tiny air bubbles so dangerous?
Because of thermal dynamics. Remember the negative 55 to 125 degree temperature swings?
Right. Yeah.
Every time the car heats up and cools down, the air inside that tiny bubble expands and contracts. Over thousands of miles of driving, that repeated expansion and contraction fatigues the surrounding metal.
Wow.
Eventually, the solder joint cracks.
And a cracked solder joint means the electrical resistance spikes, the sensor loses its connection, and you get an undervoltage fault.
Exactly. The 3D X-ray is slicing the solder joint like an MRI to catch the air bubble before the board ever gets bolted into a chassis.
It is genuinely staggering how many disciplines like metallurgy, thermodynamics, machine vision all have to perfectly align to build this system.
It is a massive undertaking.
Okay, so we've mapped out the physical physics of the failures. You've engineered specific hardware to resist those failures at the subatomic level. You've built a robotic X-ray equipped assembly line to eliminate human error. Now, according to the final stage of the documents, the DVP&Rs, you have to try and destroy the whole thing.
The design verification plan and report, yes. It is essentially an industrial torture chamber. You cannot release a system with an ASIL D safety rating without violently proving it works under worst-case scenarios.
Let's walk through these tests because the numbers here are wild. Test 1 combines environmental extremes with mechanical abuse.
Right.
They put the completed power control system into an environmental chamber and violently swing the ambient temperature from negative 40 degrees Celsius to positive 125 degrees Celsius.
But temperature's just the baseline.
Right.
While the components are baking and freezing, they bolt the entire unit to a multi-axis shaker table and subject it to a highly specific vibration profile called the VDA 320 standard.
The documents note it is hit with 35 meters per second squared of vibrational force. For context, what does that actually feel like physically?
That is roughly 3.5 Gs of constant aggressive vibration. It simulates the physical violence of driving a heavy vehicle over relentless deep cobblestones or a heavily rutted dirt road at high speeds continuously for hundreds of hours.
Freezing it, boiling it, and violently shaking it with 3.5 Gs of force.
Yeah.
And through all of that, the sensors still have to read the high voltage perfectly.
And they add one more layer of torture to test one.
Oh, man.
While it is freezing, baking, and shaking, they introduce intense electromagnetic chaos. Modern EV inverters use silicon carbide or SiC transistors.
Let's see.
These switches are incredible because they turn on and off millions of times a second to route the power, but switching that massive amount of current that fast creates massive electrical noise.
The sources quantify this noise as 10 kilovolts per microsecond of voltage change.
Which means the electrical environment inside the inverter is essentially generating a localized electromagnetic pulse continuously.
Wow.
It is deafening electrical noise. It is the equivalent of trying to accurately measure the volume of a whisper while standing next to a firing jet engine.
So the sensing hardware, the delta sigma modulators, the isolation barriers, the AURAX chips, must filter out that massive 10 kilovolt noise, survive the 3.5 Gs of vibration, endure the temperature swings, and still maintain a sensing error margin of less than plus or minus 1%.
If the voltage reading drifts by 1.1%, the system fails the torture test, and the engineers have to redesign the board.
It is unforgiving.
Yeah.
Test 2 then targets the logic systems. It applies the LV124 standard, which is designed to validate that 20 millisecond holdup circuit we talked about.
Right. They put the system under full load and purposefully crash the main 12-volt power supply down to 6 volts. They force the hiccup to happen.
Okay.
The goal is to mathematically prove that the localized backup capacitors discharge perfectly, keeping the gate drivers above their critical 13.5-volt threshold.
Right.
They are proving that the system can hold its breath under duress without triggering a false lockout.
But here's where it gets really interesting to me.
Oh, yeah.
Subjecting a metal box to vibration and heat in a lab makes sense. But the ultimate test is whether the car can execute that 60 millisecond active open circuit maneuver, that freewheeling safety net, when the voltage crashes on the highway.
Right.
You can't exactly take a real prototype car, put a test driver in it at 120 miles an hour on a track, and randomly dynamite the high voltage battery cables to see if the safety software works. It's too dangerous.
It would be incredibly dangerous and highly unrepeatable. You can't control the variables on a physical track, so instead they rely on HIL testing, hardware-in-the-loop validation.
This is where physical hardware meets the matrix. How does this work?
They take the actual physical brain of the car, the manufactured power control system board, complete with all its microchips and safety software, and they plug it into a massive, high-fidelity FPGA supercomputer rig.
An FPGA being a highly programmable logic chip that can simulate physical systems with zero latency.
Exactly. The supercomputer simulates the entire physical reality of the vehicle. It fakes the sensor, inputs the battery voltage, the motor speed, the tire friction. The physical microchip sitting on the test bench genuinely believes it is bolted inside a real car rocketing down the highway.
Wow. The engineers command the supercomputer to spin the virtual electric motor up to 12,000 RPM under maximum acceleration load. The physical chip is processing all this data, firing its virtual spark plug, so to speak.
And then the engineers inject a catastrophic virtual fault.
Oh.
They tell the system that the main battery voltage just instantly plummeted from 800 volts to 100 volts.
And this is the moment of truth.
It is.
They are watching the supercomputer's clock down to the microsecond to see if the physical chip can detect the massive voltage drop, run the plausibility math to ensure it's not a hallucination, decide that an ASIL D shutdown is required, and execute the active open circuit freewheeling command in under 60 milliseconds.
The success criteria are incredibly strict. The supercomputer monitors the physical chip's outputs. The system must execute the AOC transition flawlessly. It watches the simulated electrical currents in the motor phases. They must smoothly decay to zero without any dangerous electrical overshoots or demagnetizing spikes that could damage the motor magnets.
And most importantly, they monitor the virtual kinematics, the behavior of the virtual wheels.
There can be absolutely 0 microseconds of wheel lockup.
Wow, zero.
The supercomputer must verify that the car remains completely physically stable and coasts safely.
It is the ultimate final exam for a silicon chip. It has to save a virtual driver's life in under 1/10 of a second, over and over again, under thousands of different simulated conditions before that software version is ever allowed to be installed in a human being's driveway.
And passing that HIL test is the only way the engineering team can sleep at night knowing the math holds up against the physics.
So if I'm tracking this entire journey, it really reframes how we look at modern transportation.
It does.
We started by looking at incredibly complex, invisible points of failure. A frozen battery, unable to feed an algorithm, a 20-millisecond voltage sag confusing a logic board, or the microscopic friction on a single uncoated bolt causing a high-resistance bottleneck.
We examine how the technical architecture counters those physical failures, how high-isolation sensors use digital barriers to peer into the high-voltage environment safely, and how the lockstep AURX processors act as a skeptic, running thermodynamic power plausibility checks to weed out the false alarms.
We explore the software's reaction, the two-tier defense that tries to jog before it walks, culminating in that crucial 60-millisecond window where the car actively chooses to cut the circuit in freewheel rather than short the motor and cause a crash.
And we dug into the obsessive, almost paranoid levels of manufacturing and design prevention. Engineering temperature-immune calcium zirconate crystals, deploying robotic servo screwdrivers, measuring friction angles, X-raying microscopic air bubbles in solder, and subjecting the final product to 3.5 Gs of vibration and supercomputer simulations.
It makes you realize that when you get behind the wheel of a modern EV, you aren't just driving a mechanical object.
Not all.
You are placing your physical safety in the hands of an invisible, millisecond-fast ballet of advanced software logic, physical metallurgy, and incredibly redundant sensor checks.
It is a symphony of engineering designed with one singular purpose: to remain completely unnoticeable to the driver until the absolute exact millisecond it is needed to save their life.
Right.
But analyzing the very end of our source documents, this massive web of static safety rules raises a fascinating question about the future of this technology.
Oh, what are the documents pointing to on the horizon?
Well, this raises an important question. The engineering notes discuss transitioning to using real-time Python simulations running directly on the vehicle's computer. The goal is to continuously model the capacitor's discharge rate and the motor's load power in order to calculate dynamic FTTI margins while you drive.
Let me make sure I understand the shift here. Right now, all these safety thresholds we discussed, like deciding to shut down at exactly 150 volts or reacting within exactly 60 milliseconds, those are static rules.
Yes.
They are hard-coded into the car's brain at the factory, a fixed line in the sand.
They are reactive parameters. The car waits for the voltage to cross the 150-volt line, and then it executes its emergency protocol.
Okay.
But what if the next generation of power control systems don't rely on fixed lines in the sand? What if the car's multi-core processor is powerful enough to run a continuous real-time digital twin simulation of its own electrical and physical systems while you are cruising down the highway?
A digital twin.
Yeah.
So the car is constantly simulating its own physics in the background. It knows its exact speed, the ambient temperature, the degradation level of the battery chemistry, and the exact resistance of every busbar joint.
Precisely. By running those physics simulations, the car could predict exactly how many milliseconds of safety margin it has at that specific second based on the current dynamic conditions. It wouldn't just wait for a loose bolt to cause a voltage drop and then react. It could simulate the degradation of that joint. Realize that a transient voltage sag is highly probable if you accelerate hard and dynamically adjust the FOC algorithm's torque request to prevent the under-voltage failure from ever physically happening.
That is an incredible concept. To use a medical analogy, the car wouldn't just be waiting to read an X-ray of a broken bone and then putting a cast on it.
Right.
It would be constantly analyzing the structural stress on your bones as you run and subtly shifting your weight distribution for you to ensure the fracture never actually occurs.
Exactly.
It takes this dense reactive diagnostic landscape we've been talking about and turns the car's computer into a predictive crystal ball.
The invisible safety net stops being a net that catches you when you fall and becomes an active system that stops you from losing your balance in the first place.
That is a phenomenal thought to leave on. The idea that the future of automotive safety engineering isn't just about building faster processors or stronger components, but about programming cars that can literally foresee the consequences of their own physics before reality catches up to the math.
Yeah, it's exciting stuff.
Thank you for walking through this incredibly dense, fascinating world of systems engineering with me.
Yeah.
The next time you press the accelerator in an electric vehicle, just take a second to appreciate the millions of calculations and perfectly coded bolts working beneath your feet just to keep those wheels spinning smoothly.